So we're continuing with our lecture on software specification methods. Again, we've in the last lecture we looked at some basic software specification in natural language, flowcharts, state transition diagrams, and structure charts. Now we're looking at finishing this up with data flow diagrams. In fact, we're going to look at some real-time data flow diagrams and then Petri nets and state charts. I want to stop a little bit and give a view from above here on why we're talking about these things and how they're important and relevant. We have a few what are referred to as informal specification methods. And what these are is these are methods for software engineering that are intuitive to non-technical people. Problem is they're difficult to prove anything. And these methods that are called informal are things like natural language. Okay, using natural language is really important. It's a great commenting, for example, and to just help describe problems in design. And we use this all the time in doing requirements analysis and that sort of thing. Again, in commenting code and commenting design. Flowcharts are another one. They're very common. They show the flow of, the flow of a program, but they're not rigorous, and we've already seen from those descriptions, right? They have some problems. Structure charts is another one. There are things that are semi-formal specification methods. These two are easy to learn. They do require some training. They're not quite as natural as natural language. Of course, it's just using spoken language, or written language, and flowcharts. These things are natural and easy to use. But the semi-formal methods, they provide some rigor. That means you are going to be able to use them in some rigorous ways to at least maybe not do rigorous proofs, but can definitely come up with some bounds and some results. Data flow diagrams are an example of these semi-formal specification methods. As we will see as we move on. And then there are formal specification methods. These tend to be difficult to learn, but they're rigorous and provable, and that's the key, is that they provide some good mechanisms to really, they have a valid logic associated with them, its syntax, etc. Now, examples of the formal specification methods include state transition diagrams, which we've already seen state transition diagrams, but also Petri nets. And Petri nets are one of the more arcane formal specification methods. Not a lot of people use them in real applications, but they're great for theoretical explorations on, again, rigor and provability. And then finally, state charts, which actually are really a valuable and rigorous approach for software specification. Okay, but we're going to focus next on these data flow diagrams because they're not only useful in general for real-time systems, but they map, we're going to see that they map very well to the Chimera methodology, which you've read about, and of course that's implemented, that carries through in our PBORT operating system, which you'll be finally getting to in the lab. Okay, so data flow diagrams. What these do is they analyze data flow through the system and to determine the major functions, right? So again, unlike flowcharts, which is program flow or flow of execution, this is the actual flow of data. Now, it can show concurrency explicitly, but does not show synchronization. Some people say there are some implicit forms of synchronization that it can show, but fundamentally the syntax of these is that circles represent processes. So these are basically things that transform data. And then rectangular boxes represent sources and sinks of data. Double parallel lines is a data store that's like a variable or a persistent database or data record. And then there are arrows that represent data flow. Okay? Now, here is an example. This is taken out of the LaPlante text. Again, this is an example of a helicopter attitude control system that we've talked about frequently in a familiar way, but this is actually now we're talking about a specification. There is in the LaPlante text, there is a text version of a natural language specification for the helicopter, this particular helicopter attitude control system. And but the bottom line is, here are some of the details are that there's an accelerometer and a gyro, and these are compensation. These are our approaches, again, because they are circles, they represent data transformation. And so that is these guys up here. Here's the acceleration compensation, accelerometer compensation, and the gyro compensation. So these are part of an inertial measurement unit for the helicopter. And inertial measurements are very common. Measurement units, IMUs, are very common. A sensor in military and aircraft, they provide a lot of information for prior to GPS. That was the main source of integrating that data to figure out where aircraft were. And now those just augment GPS, which give an absolute metric. But what happens here is the accelerometer produces raw data, which then gets compensated and is put in a data store. And so the compensation process is basically tries to correct for some drift and errors in the IMU. Now, so there's a compensation process for both of these, and they go into data stores. And then the compensated data is actually used to calculate the position of the position and attitude, in fact, of the helicopter. And we see that that goes into also a data store. Again, it has the position, the attitude, the gyro value, and the accelerometer value. And now what happens is that data then goes back to some torquers for the gyro to actually give the gyros, and these are in the days of mechanical gyros, and so they were literally, these are spinning masses, and so they have to torque them for because they're not perfect. They have friction, they lose speed, and so they're basically commanded to correct it, I guess I should say. And so then that's a process where you have some gyro data, then there it is. Commands are developed through, again, a data transformation, and this is now a sync, where again this is a source of data because these are sensors. This is a sync because the torque commands go to the gyro, give it a little kick basically to keep it going. And then likewise, this information on position, attitude, and acceleration are updated on the screen for display to the pilot. Okay. Now, a few details again on the data flow diagram, that the synchronization of the compensated data is only implied from the natural language description in the LaPlante text. Okay, but this is a pretty accurate of what they're trying to describe in there. Now, one additional thing is that you can use hierarchies of data flow diagrams to provide additional process details. Okay, so you could imagine a process. One of these circles actually consists of a data flow diagram, its own little sub data flow diagram, to give more detail on what's going on inside that data transformation, for example. And keep in mind, the data flow diagram describes what the system does. It does not describe when. Okay, that's an important distinction. Now, what what I have here is, again, helicopter attitude control is a common problem to study in real-time systems. And so up here we see that this is taken from both the Phil LaPlante description of the problem, but also the J.C. Cooling's book on providing some additional fixes, even though this diagram matches the description in LaPlante to some degree. There are some bugs in it. And so the actual description is a little bit more, first of all, it matches the description from the cooling text of what's really happening here. It eliminates some redundant stores, and then the acceleration input to the torque gyros data transformation actually matches the natural language specification more closely to the way it's actually described in the LaPlante text. Again, this is the actual diagram LaPlante presents. This one is corrected to better match the natural specification, and with some additional hints from the cooling text. Okay, so here you can see the differences. Whoops, went the wrong direction. There are some subtle differences here. Again, the accelerometer data comes in, it gets compensated and goes out to a data store. Likewise with the gyros, that's the same. And these do go in to calculate the position, which provides position and attitude data on for the helicopter. However, right, the description says that torque gyros actually gets the gyro data and the acceleration data comes in to compute, to do this data transformation, to provide commands to the gyros. Again, this is a sync, this is a process. So both of these values, there's no point in carrying those raw values through to here. We have them in these data stores. That applies the torque gyros. This is and again, this is how cooling describes this more accurately, that yeah, instead of just duplicating that, we're going to refer to directly from this data store to provide that update. So you've got the position and attitude information plus the Excel data that goes into the screen display. Okay, so again, some bugs in the Phil LaPlante text. These correct them. However, when you think about this, this is simplified. There's another question, which is, well, how does it probably really take place on an actual helicopter? And the issue here is, what is the value of those data stores? And so this is what I refer to as the doubly improved data flow diagram for the helicopter attitude control system. Again, this is a combination of LaPlante and cooling, but also adds some information about what's really likely going on. That it does make it clearer, and I think in the description in the text it was left out just to simplify, but in fact this compensation of the accelerometer is based on not only the new value but also on the old value. So this is kept in a data store, so it was read in a previous time step. Compensated value is then dumped into the data store, and now this is historical. When we get a new reading here, it uses that old reading plus the new readings, right, to provide a compensated data. And then, of course, that still goes there. And then we get the same thing that when we're calculating the position, because these are incremental, to calculate the position, we have to know what the old value was. And so, because again, these are derivatives of these values, and so they're updates to the old value. So that's a couple of extra things that are just reminding us why these things really are there. And again, it's reinforcing their existence as true data stores, not just temporary variables. Because again, a temporary variable generally doesn't raise itself to needing a data store, which again is a persistent storage of a value. Okay,